Welcome back. As advertised in the bold yellow type there, this will be a very superficial review of electric and magnetic fields. Consider it a broad survey with no depth. Many of you have not yet taken a class in electromagnetism. Don't sweat. In that class, you would learn how to calculate electric and magnetic fields, often using the derivative and integral calculus. That does not concern us in this class. We don't need to know how to do that. But you do need to know the meaning of the electric and magnetic fields. So that's what we'll be looking at in the following slides. This cool GIF here is demonstrating the phenomenon of magnetic induction, which is described mathematically by Faraday's law. That's one of the four so-called Maxwell equations, which we will discuss extremely topically. A lot of you, like me, probably first learned about electric charge back in grade school. I was presented with this cartoon picture of positive and negative charges making up the atoms of the universe. And maybe you were told that the electrons orbit the nucleus, and the nucleus has these positive particles in them called protons. Here's a slightly more sophisticated picture. This is the planetary model of an atom, first posited by Niels Bohr, whose research, by the way, was financed by beer. That's an interesting story. A Danish brewery, I believe, was the source of his family's wealth. The Bohr model of the atom is something that we will look at in detail towards the end of the semester. We will actually use that model to calculate the spectrum of the hydrogen atom, meaning the colors, or the various wavelengths emitted by the hydrogen atom. But we know now, in fact, we've known since about 1920, 25, that even this is really a rather naive picture of the hydrogen atom, or any atom for that matter. Can you guess where I got this? Of course, it's the Falstad website. Here is a three-dimensional visualization of the probability density of the electron in a hydrogen atom. So where the color is more dense, you're more likely to detect the electron. So the modern description of atoms is much richer than those cartoon pictures of the Bohr atom would have you believe. This is a topic we'll return to later in the semester. I'm already going off topic. We're here to talk about electric charge. Have you ever wondered where that word comes from, electricity? Well, evidently, the word electric or electron comes from a Greek word that meant amber. And I wasn't even totally sure what amber was. I'd seen it in Jurassic Park, right? That fictional story about extracting DNA from a mosquito inside a chunk of amber and then using the DNA to recreate or clone dinosaurs. But, okay, Wikipedia tells me it's a see-through fossilized resin. And it must exist all over the world, and people in the Greek region were familiar with it. And it has an interesting property which we should talk about.
The first recorded experiments were of rubbing amber on cat fur. Here we are reproducing this experiment using amber and some wool. How this works is known as the triboelectric effect, and this has to do with something called electron affinity. Electron affinity is where the substances can hold on to extra electrons or not. Amber is a material that responds very well to this rubbing. See how the bits of paper stick to the amber. A better substance to play with is a man-made substance called ebonite. We can look at this effect easier by looking at two sticks of ebonite. One of these is suspended by a piece of thread, and the other is brought towards it. As the two ebonites have the same charge on them, they repel from each other.
Here's the etymology of the word electric, if you're into that sort of thing. In fact, if you look at the Greek word here for amber, you can actually spell out what looks like electron, because I don't know about this first letter, but the second letter is lambda. Lambda starts with L. I think lambda is like the English letter L. Is it an English alphabet that we have? Roman alphabet? I forget. So L and then epsilon, that's like E. What is this? Kappa has a K sound. Tau is like T. And then rho like R. I don't know how you say O in Greek. And there it is. That looks like the letter V, but that's actually nu, which is like N. So you can actually spell out electron there, or electron. Whoa. Well, if you're not familiar with this behavior, you can take a bunch of different materials, rub them together, and experience what we call static electricity. You feel that crackling sometimes in a wool blanket, or if you walk across carpet and touch a doorknob, you can feel that shock. And as the guy in the video explained, that's called the triboelectric effect. The fact that some materials have a greater affinity for charge than others. And so it didn't take long after experimenting with this effect for this model to arise, where we think of charge as having two flavors, kind of. It's either positive or negative. That's all you need to explain the effect. And that means when you rub these various materials together, you either get repulsion between them or attraction. This is not a class in electromagnetism, so we'll keep this short, but let's let Bruce Yeany say a word about the triboelectric effect and give us a demonstration here.
Now, wood is actually a very good insulator. In this case, I have an 8-foot 2x4 hanging from the ceiling. And the charge on it is neutral, but we're going to see if we can move it with a static charge. Now we'll get a nice charge on our PVC pipe here and see if we can move it. Okay, there it goes. See if I can reverse directions. With induction charging, I don't have to touch the pipe to the wood. I just have to bring it near it. Let's try it on a smaller scale. Here's a positive charge brought near some little dots of paper. Let's see that again in slow motion. Now let's go back to that moving of the can across the table. Here we'll try the can with an uncharged PVC pipe. Nothing happens because both objects are neutral. Let's put a charge on it, and now I can pull the can across the table. Now we also have a polarization of the electrons inside the can. Since the can is a metal and a conductor, it allows the electrons to move away from that negative charge, allowing the positive charge of the can to be attracted to the PVC pipe. The electrons aren't bound to stay with the atoms like they are with an insulator. Now we can also try this with a positive charge. In this case, the electrons are free to move towards the positive charge of the glass.
Now, if you were a scientist working hundreds of years ago, and you had established that this quantity electric charge comes in two flavors, positive or negative, and that like charges repel and opposite charges attract, you might then start to wonder, how does the force of attraction or repulsion depend on the distance between the two objects? And so the classic experiments were done, I think, with something called pith balls. To this day, I really don't know what pith is. Think of it like styrofoam balls that had charges deposited on them. And experiments like you see here in this GIF were used to determine the forces between those pith balls based on their separation. And it wasn't long before somebody discovered that the attraction or repulsion between them obeyed an inverse square law, just like gravity. So if you had two pith balls which were charged and you put them twice as far as they were originally from each other, you'd find that the the attraction or repulsion was now 1/4. 10 times as far would mean 1/10. Excuse me, 1/100th. That's an inverse square law. And from what I've read, despite the fact that we call this result Coulomb's law, Coulomb himself was not the one who discovered it. Somebody else figured this out. But Coulomb's law says more than just that the attraction or repulsion obeys an inverse square law. It also says that the force is proportional to the two charges individually. So if you double one of the charges, you double the force. If you triple the other charge, you would triple the force. If you double and triple the two charges, that would be 6 times the force. It's a lot like gravity. So instead of masses, we're talking about charges. Now, this number out front here, this is an experimentally determined constant of proportionality. It's something you would have to measure in a lab. And this was probably measured for the first time hundreds of years ago. Now there are incredibly precise measurements of this quantity. And you might be interested to know, there's another famous Coulomb out there. Trader Joe is actually Trader Joe Coulomb. Almost the same spelling. He's got an extra E on the end. This constant of proportionality, which describes the strength of the attraction or repulsion between charged objects. Like I said, it's been measured. There's another way to write it. You can cast it in a different form by setting it equal to the reciprocal of 4 pi epsilon naught. This quantity here is epsilon naught. We also call that the permittivity of vacuum. And the reason for calling it the permittivity, we don't really have time to talk about that, but it's worth knowing that word. So, measuring K in a laboratory is equivalent to measuring epsilon naught, the permittivity. And here's a modern value for that number. Nope, I take that back. This is actually K. Yeah, later I'll write down the value of epsilon naught. You can see this is almost 9 billion. So take the reciprocal of that, multiply by 1 over 4 pi, and you would have the value of the permittivity epsilon naught, which we'll get to. And I'm emphasizing this quantity because it shows up later when we talk about electromagnetic waves, which is, of course, the reason why we're reviewing electric and magnetic fields. Vacuum electric permittivity. There's the fancy name for epsilon naught. Just make sure you understand it's something you can measure. You look at the force between charged objects. That's where you get that number from. Well, it's not much of a conceptual leap to go from talking about the forces between charges to this thing called the electric field. So imagine you have one electric charge, a positive one, located right here at the origin. And then you imagine taking a second positive charge and placing it at all these different locations in the XY plane and measuring or predicting, calculating the force that would be applied to that second charge. So if you had a charge sitting right here, and you put a second one over here, for instance. Well, part of the content of Coulomb's law is that the force between the charges is along the line between the two. So here's the line joining the two charges. I've got one charge at the origin and another charge here. It's not like the charge here gets pushed that way or this way. It gets pushed directly away from the other charge. So these arrows tell you the direction that a second charge would be pushed if it were placed at that location. And it's clear that if you put the second charge farther away, it won't be pushed as hard because the force between them obeys an inverse square law. And that's what this vector field is showing. The arrows are made shorter and shorter to represent the fact that the strength of the interaction decreases with the inverse square of the distance. That's why these arrows get short so quickly as you move away from the origin. So that's one way of thinking about the electric field around a point charge. Again, the charge isn't drawn in this graph, but take this charge, put it right there. These arrows, these vectors, tell you the effect that would be had on a second charge placed anywhere in the neighborhood of that first charge. And those arrows are the electric field. That's what the electric field is. That's one way of thinking about it. It shows you the influence on a second charge due to the presence of that first charge. So we can see in here, or in this picture right here, that electric fields, or I should say the electric field, diverges away from a point charge. If there's a charge in space and you look at the field around that charge, it looks like it's diverging away from that point. And in other words, you could say that there's a positive divergence at that location. Well, then we can get more sophisticated and imagine we've got two so-called source charges. So if you had two negative charges sitting here, what would happen to a third positive charge placed anywhere in the xy plane? So if I plopped a little proton right there, for instance, well, it's going to be attracted to this charge. It will also be attracted to this charge. The net effect of those two forces is an attraction in this direction, tangent to the curve right there. And that's what these field lines show us. They show us the direction of force, net force, on a positive test charge placed anywhere in the xy plane. Now, we can't actually visualize, I take that back. I was about to say you cannot visualize the strength of the field because in the previous plot, we had all these different arrows, and the length of the arrow told us about the magnitude of the force on a positive charge that would be placed there. So we don't have vectors in this instance, but there's another way of visualizing the strength. It has to do with the density of the field lines. Do you see how bunched together the field lines are here? That tells you that the field is stronger in magnitude than it would be out here where the field lines are more spread apart. Now you get a similar picture for a positive and a negative charge placed near each other. And this is very intuitive. Doesn't it make sense that the electric field right here would point to the right? Because, again, the electric field tells you what would happen to a positive charge placed at that location. A positive charge placed right here would be pushed away from this one, so pushed to the right, but it would also be attracted to the negative charge. And those two effects add. It makes sense then that the electric field at this location points to the right. It also makes sense that the electric field is stronger in the vicinity of either charge, and it gets weaker out here. You can see the field lines are spread apart. By the way, this configuration, a positive charge and a negative charge in close proximity, that is called a dipole, an electric dipole, because it has two poles. Yes, I got this from the Falstad site. Like I said, endless hours of fun on that website. There's so many different simulations to play with. Here's the field around a quadrupole. You can count them, 4 charges, 2 of each sign. That's a more interesting electric field. What does the field tell you? Well, what can we infer from this? The direction of the arrows tell you the direction that a 5th positive charge would be pushed if it were placed at that location. So right here, for instance, since the arrows point down, I know that if a 5th charge were placed right here and it were positive, it would be pushed downwards. If a negative charge were placed right there, it would be pushed in the opposite direction. So negative charges are pushed opposite the electric field. And probably the strength of the field in this visualization is signified by the brightness of the arrows. You can see that the arrows are fading away to nothing as we move away from the quadrupole. So there are different ways of representing that information, the direction and the strength, in different types of graphs. You can go to this website and even look at 3-dimensional electric field distributions. So here are 2 rings of charge. You have to imagine electric charge distributed around this ring, 2 rings. And this says a charged ring dipole. So one of these rings must have positive charge and the other ring must have negative charge. And if you go to the site, you can actually click and drag that and look at it from different angles. You can change the resolution, all sorts of stuff. Here is an actual demonstration of an electric field distribution. And no offense to James Lincoln, who made this video, but I apologize for the music. Here's what we would call a uniform electric field, which is one that has the same value at all points in space. So you have to imagine, well, this picture is showing you that right here, the electric field points to the right, and it has a strength represented by the length of this arrow. And you can see that the electric field at this location is the same because it points in the same direction with the same strength. So the locations at the tails of all these vectors have the same electric field, but we can infer that it's supposed to be that way throughout the screen here. So pick any arbitrary point and the field would point to the right with a strength represented by the length of all of these arrows. That's a so-called uniform electric field. And let's launch a charge into this region, a positive charge. We know that the electric field pushes on the charge in the direction of the field. F equals ma tells us that if the force is to the right, then the acceleration must also be to the right. So you could use Coulomb's law to calculate that force, and then use the mass of the charge, and F equals ma to calculate the acceleration. And I just made a bunch of slides here and strung them together. Let's look at the very simple dynamics of an electric field which has been launched into a uniform electric field. Did I say an electric field? An electric charge. Let's look at the dynamics of an electric charge which has been launched into a uniform electric field. Okay, that took me a while, so I'm going to do that again. And now I'd like to look at the units, the dimensionality of this quantity called the permittivity of vacuum, because we will need this shortly. In a future presentation when we look at electromagnetic waves, we need to know the dimensionality of this quantity epsilon naught. And that's easy to infer just by looking at the units on both sides of the equation. We know that force is measured in newtons, and look at what we're plugging in. Charge is measured in coulombs. At least that's the SI unit of electric charge, the coulomb. And I guess I'll just throw this out. 1 coulomb is an enormous quantity of charge. You know when you walk across carpet and you touch the doorknob and you receive a little shock, or you get out of your car after you've been driving for a while and your arm touches the door and you get a little shock? That quantity of charge is way less than a coulomb. You would not want 1 coulomb jumping from your fingertip to a doorknob. Okay, so we have coulombs squared in the numerator, meters squared in the denominator, but we need newtons to come out. So after plugging everything into this formula, newtons needs to be the output dimensions. And so it's easy to conclude that this quantity in front, this constant 1 over 4 pi epsilon naught, which was previously called K, it must have the dimensions of Newton meters squared over Coulomb squared. That way the meters squared cancel the meters squared, and same thing for the Coulomb squared. Well, epsilon naught is in the denominator, so the dimensions of epsilon naught would actually be the reciprocal of these dimensions. 4 pi is unitless, dimensionless. It contributes nothing. So we just take the reciprocal of these units, and there it is. So you don't have to memorize that, definitely not. But I'll bring this slide back in a future presentation when we combine the units of permittivity with the units of another important quantity, which we'll look at. If you're curious about the value, there it is. As you saw on Wikipedia, this constant has actually been measured with much greater precision nowadays than just 3 sig figs. But these are the 3 sig figs that I have memorized. Remember, K was something like 9 billion. And epsilon naught is more or less the reciprocal of K. So it's not surprising that it's a very small number. Let's move on to magnetism now, because I really just wanted you to be comfortable with the meaning of an electric field, not how to calculate it. So have you ever wondered where the word magnet comes from? It looks like there's a region in Greece, which used to be known as Magnesia. Is that the same thing as milk of magnesia? I don't know. And in this region, it was common to stumble across these rocks called lodestones that had a very interesting property. It must have been particularly mysterious to people back then. Even to people nowadays, magnets are incredible, right? And, well, they didn't have paper clips back then, but they probably had chunks of iron. Was this before or after the Iron Age? But it was discovered that these chunks of rock called lodestones had an affinity for iron. There was an attraction there. So this must have captivated the imagination of anybody who was lucky enough to come into contact with a lodestone. And they even made compasses out of them at the time. So there you go, magnets, magnesia, thousands of years ago even. So check it out. Here's a modern incarnation of an ancient compass design.
Good morning from Admiral County, Virginia. Today we will be looking at the Chinese compass, which you can see here on the right. You might be used to seeing compasses that look like this. This compass has a needle in the middle with a small magnet that aligns with the Earth's magnetic North Pole, which is different from the true North Pole or geographic North Pole. As you spin the compass, you can see that the arrow stays oriented, pointing towards the magnetic north. So when you line up the tip of the needle with the N on the outside of the compass, you can see where all the directions are. Many cell phones also have a compass app on them. This compass app shows what direction the phone is facing. So I'm facing east. You can tell because it's morning, the sun rises over there, and now it's over there in the sky. It's winter, so it stays pretty low the whole time. This compass works the same way. As I turn it, the red arrow pointing toward north stays in the same spot, and the line telling you which way the phone is facing is moving. So right now, the phone is facing to the south. Now let's look at our Chinese compass. A Chinese compass works in a very similar way. The needle here is not within a case, and it's placed on this metal plate. No matter how you place the ladle, the stone inside is orienting itself with the Earth's magnetic poles. Ancient Chinese compasses were made out of lodestone, which is a naturally magnetized piece of the mineral magnetite. The Chinese compass was actually designed for the handle of the ladle to point south. So you can see the spoon side is pointing north, the same as our compass, and the ladle side is pointing toward the south. The Chinese did not use their compass for navigation at first. They used it to find the direction so that they could orient their spaces using the magnetic directions.
Place the bar magnet on the float. Allow it to settle. The magnet turns the float and settles in a particular direction. Note the directions. Pick the magnet and turn it around and see what happens. The float turns again and settles in the same direction.
So I've actually done this demonstration, and if you turn this magnet 90 degrees away from north, so point it east or west, you can actually feel Earth's magnetic field torquing the bar magnet. There's a noticeable tug against your fingers. I have got to get myself one of those little Chinese compasses and a case to put it in, because otherwise I'll definitely lose it. So now we have a partial answer to the question, what is a magnetic field? In practical terms, you could say it gives you the direction along which a compass needle will line up. Now, that doesn't really tell you what creates a magnetic field or why it is that the compass needle makes itself parallel with the field, but you could say it's an operational definition. So what does a magnetic field tell you? Well, one thing it tells you is the direction that a compass needle will point. Let's let Professor Boyd, the necktie guy, as I like to call him, show us a little bit more about the meaning of magnetic field lines.
I've got a bar magnet on the table here. Its north pole is denoted red, south pole green. And I've also got a compass. Compass is useful for finding the direction of the Earth's magnetic field, obviously. That's what it's for. But you can also use it to determine which pole is the North Pole or the South Pole if you don't know previously. The North Pole, the magnetic field lines emanate from the North Pole. So they come out of the North Pole, come around the magnet, and then into the South Pole. And I can demonstrate that using this compass. The direction of the needle on the compass is given, this red portion of the needle indicates the direction of north. And so when I bring this compass near the North Pole, it doesn't point, the north part of the compass doesn't point toward the North Pole, but instead points in the direction of the magnetic field. So that's the important point for this demonstration. The direction that the compass needle points, the red part of it, is the direction of the magnetic field. And just so you understand how it works, this is the North Pole of the magnet and the South Pole of the magnetic compass needle. This South Pole is attracting the North Pole of this bar magnet. So if we then want to investigate how the magnetic field direction changes as we move in the vicinity of this bar magnet, now we've moved here and we can see that the magnetic field lines are starting to curve. At this point, the magnetic field lines have come out here and are going in exactly the opposite direction.
Let me interject here. If you could actually see those magnetic field lines or curves, the compass needle would always point in the direction of the tangent line to the curve.
And then once we've are down by the South Pole of the bar magnet, the magnetic fields are again pointing in the same direction that they were over here. So the magnetic field lines look like they come out here, come around, and then in here. The same thing on the other side. Come out, around, and then in on this side. But the compass needle points in the direction of the local magnetic field. This is a model of a similar thing. It's a bar magnet in the center with the North Pole denoted by red and the South Pole denoted by blue in this case. And each of these little red things are tiny little compass needles. And they give the same information that we got before. Get this one out of the field. So we got a compass needle pointing this way, meaning that it's the magnetic field is that way, around, and then in to the South Pole, as denoted by all these little magnetic compass needles.
So you're really looking at an actual physical realization of a vector field. Those little tiny compasses encased in the plastic are showing you the direction of the field at each point. As you'll see here, it's not just little compass needles that line up with the magnetic field.
Okay, here we do. We've got a stack of magnets underneath, a stack of rock magnets, and we're going to put iron filings over the top here. And we finally got a piece of paper that's not glossy, so this ought to be easier to see. All right, there's our magnetic field lines. As I tap it, they kind of align even better, especially on the outside. Things to notice. Which side is north and south? We could figure out with a compass. That south is attracted to a north, and north attracted to the south. Now, which one is which is really rather irrelevant. You'll notice in the center that they go straight across from north to south. Then they also go on the outside from north to south in these big arcs. Now with my hand, if I was doing right-hand rule, magnetic field lines go outside of norths and into souths. Now what about here? It's doing the same thing three-dimensionally right alongside the magnets. And we can actually show this three-dimensionality of it just like that.
So as he just described, for this particular magnetic field, the field lines make closed loops. They point from south to north, they swoop out the North Pole, they come back around and enter the South Pole again. That's true throughout the distribution of the field lines. So this is very different from the previous situation where I was talking about an electric field diverging away from an electric charge. In that case, you had all the lines pointing outwards from a common source. And also in that case, you could actually draw an imaginary circle in space and you would find a net number of lines piercing that circle and pointing outwards. Here it's very different. If you were to draw a closed circle in space, any line that pierces and goes into the circle will also pierce and then go out of the circle, which means the net number of lines going in or out is 0. For every line going in, there's a line going out. And that ends up being a fundamental feature of magnetic fields. There's no way around it. You can never produce a magnetic field such that an imaginary circle would have a net number of lines diverging from the region within the circle. And the way you say that in vector calculus is that the magnetic field has 0 divergence. The divergence of the field is 0. And that's related to the following physical fact, which you may be familiar with. I wish I could go back to an actual picture of a magnet. Let me do that. Back to Professor Boyd's magnet. He said that the red end was north, the green end was south, and experimentally you would find that any other magnet would have its north pole attracted to this green south pole, and the other magnet would have its south pole attracted to the red north pole. So north attracts south and vice versa. So you might be thinking, well, how about we just break the magnet in half and isolate the north pole? And then we would find that that north pole is always attracted to the south pole of another magnet, and it's always repelled by the north pole of another magnet. But it ends up being more complicated than that. It's kind of surprising, but when you break the magnet in half, it still behaves exactly like this original magnet. You would still find that it had a north pole and a south pole. And that is related to the fact that I just mentioned, that the magnetic field has no divergence. The fact that breaking a magnet in half produces 2 magnets, each of which has its own north and south poles, that means that you're always going to find a field distribution around any magnet such that the lines that pierce out end up piercing back in. That's a fundamental difference between the magnetic field and the electric field. With electric fields, it's possible to isolate just a plus charge or just a minus charge and have those field lines all pointing away or all towards the charge, depending on whether it's positive or negative. Not so with magnetic poles. So we put that into words by saying that as far as we know, magnetic monopoles do not exist. A monopole would be an isolated north pole or an isolated south pole. So magnets are always dipoles. They always have a north and a south. Is there a giant bar magnet at the core of the Earth? Of course not. This picture at least got the fact that the Earth is round correct. But despite the fact that there is not an actual giant bar magnet at the center of the Earth sure behaves like that. When you look at the magnetic field distribution in the neighborhood of the Earth, it looks a lot like the field distribution around a dipole, a bar magnet. And a commonly misunderstood feature here is that bar magnet really has its north pole near the Earth's south pole. In fact, if you just Google planet Earth magnet, you'll get some graphics where they goof this up and they get it backwards. You see if the field lines swoop out of the north pole of the magnet, they end up pointing this way over the surface of the Earth. So if you were living near the equator, remember the field lines tell you the direction that the little compass needle will line up. And so the red tip or the north tip of the compass needle does point towards the Earth's geographic north pole. See how that works? So the dipole associated with Earth's magnetic field is actually opposite the way we think of true north and true south. And if you're wondering, well, then what the heck is north? If north isn't the direction of, because you'll also notice that the axis of that dipole is displaced from the rotational axis. So the real definition of north is if you were at the North Pole and you looked right over your head. Actually, that's not even going to explain it. So the Earth rotates, right? Once a day, roughly, it rotates. and the axis of rotation points in a particular direction called north. And there's a star Polaris that happens to be almost in that direction. So if you look at that star, you're facing north. So actually, facing Polaris, the North Star, is a better way to find north at night than using a compass needle. Depending on where you are, the compass needle might be off by 10, 15 degrees, and it's changing all the time. So the Earth's magnetic field, that's a very complicated topic. I don't know a whole lot about it. The nature of the source of that field is rather mysterious. There's a Veritasium video on this subject that might be worth checking out, but this is an active area of research. How does the core of the Earth create that field? And I know it does involve the flow, the bulk motion of molten metals, because we know metals have free charges in them, and we're going to see that moving electric charge really is the source of a magnetic field. And that brings us to the famous Oersted experiment. According to legend, Oersted was a high school teacher who discovered this behavior unexpectedly during a classroom demonstration. Okay, what did we just see there? When the power supply is off and there is no electric current flowing through this metal rod, the default orientation of this magnetic needle or compass needle is to line up with the Earth's magnetic field. But as soon as he turns on this power supply and forces charge to flow through the rod, you see that the orientation of the compass needle changes. Well, if compass needles respond to magnetic fields, then there must be a magnetic field in the presence of this current-carrying rod. So that was a major revelation at the time in science, because prior to that discovery, it was thought that magnetic fields were only produced by magnetic materials like those lodestones, the magnetite. And here suddenly it was discovered that electric currents influence compass needles. So electric currents must somehow be associated with magnetic fields. And I'm sure there was immediate active interest in how currents produce fields and calculating that. So speaking of electric current, I kind of skipped over something there, but there's no reason people in the 1700s, certainly before that, should have known that this phenomenon of electric current was somehow related to static electricity. Again, lightning, when you feel the crackle in a wool blanket, when you shock yourself on the doorknob after walking across the carpet, we think of that as static electricity. And that was also a major discovery, to realize that electric current involved the flow of those same charges. And whatever mental pictures people had or scientists had at the time to explain that, it must have taken a while to refine it to the picture that we have today of electrons, for instance, flowing down this metal conductor. And so now, of course, I've got myself wondering, well, how did they discover electric current? What did that look like to them back then if they didn't know that it was flowing electric charge? I suppose people probably stumbled across batteries in chemistry. They managed to develop crude electrochemical cells. Maybe they figured out how to turn on a light bulb. Yeah, that must be an interesting thing to investigate. How did scientists discover electric current before knowing that electric current was actually the flow of these electric charge carriers that are also associated with static electricity? So I don't know if you noticed there, but when he ran the current the other way, the compass needle pointed 180 degrees, the opposite direction. So evidently, the direction of flow of current has something to do with the direction of the local magnetic field. So now we're able to say something a little bit more substantial about magnetic fields. Instead of merely observing that a magnetic field line shows you the direction that a compass needle will point, we can say something about the source of magnetic fields. We've just seen that electric currents establish magnetic fields. If they didn't, you wouldn't see that compass needle move as soon as you turned on the power supply. Here's another demonstration of that electric currents can be a source of magnetic fields. So what's the compass needle doing right now? Its default orientation is to line up with the Earth's magnetic field. So that needle would be pointing approximately north. Watch what happens when he forces electric current to flow through the wire. So now he's going to switch the polarity of the battery, which means he'll force electric current to flow the opposite direction through the coil. Okay, and of course it points the opposite direction from the way it did before. Previously it pointed right, and now it's pointing left. And it doesn't need to be a compass needle that shows us how an electric current establishes a magnetic field in the vicinity of the coil.
I'm now going to sprinkle on some iron filings onto the plastic sheet. The iron filings are randomly oriented. When I apply a current to the coil, a magnetic field will be generated. This magnetic field will magnetize the iron filings, and they will rotate and align along this magnetic field. So now I'm going to apply a current, and I'm going to tap to help the filings align along the magnetic field. Inside the coil, the iron filings have all rotated to align along the length of the coil. Let me zoom in on this end. So you can see how they've aligned, and as they exit the coil, they quickly spread out and the field becomes weak and the filings outside the coil do not rotate. These magnetic field lines that are exiting the coil here on the left end will have to spread out and circle around and come back in the right side of the coil.
Let's do just a couple more here.
Just the coil of copper wire. There's about 15 turns on this. I'll connect up the terminals. Okay, I'll probably zoom in a little closer on this one. And we'll press the Morse code, tap a key, and see what happens. Here we go. Oh, wow. Okay, I'll just press it again. Okay, let's see what's happened. Well, we can see that the iron powder's lined up down the centre here, and then we're still getting this sort of circular shape around. Let's just have a look, remember what it looks like, where it's going through the plate there. And we're starting to get some circular shapes, especially up close. You can see that it's forming circles, and then it's sort of an offset circle here and on the other side. So what's this indicating? So magnetic field lines are straight down the centre, and then it's starting to curve off and then start to form circles close, and these ones are running out, and then we've got this evenly distributed powder at the edges. Okay, well, let's look at the third one, see what that looks like. Just disconnect the I'll bring in this coil, we'll zoom out a little bit. Just remember what this one looks like. It was a set of 5 coils, and each one of these has about 15 turns on it. Now, it's a little bit dark, so I've got a light source on the side here. I'll just bring it in a little bit closer. It brings up the contrast. And we'll connect the power supply to the terminals. And okay, we'll press the Morse tapper key and see what happens. Okay, so we can see down the centre here, we've got the iron powder lining up. It's curving at the edges. Let's zoom in a little bit closer.
We have a pretty satisfying answer now to the question, what creates magnetic field? What's the source of the magnetic field? Because we've seen that current carrying wires, electric current, will establish a local magnetic field. We still don't know, however, why a compass needle points in the direction of the field. So the other half of the investigation would be what causes a little iron filing or a compass needle to be influenced by a magnetic field. This demonstration should make it fairly clear that not only can an electric current produce a magnetic field, an electric current is also influenced by a magnetic field. In fact, this current carrying wire experienced a force from the magnetic field. The magnetic field was being set up by this permanent magnet here, and it was the wire that was experiencing the force. So it's almost like we flipped everything inside out. We started out this presentation by talking about lodestones and how these natural magnets produce magnetic fields. Refrigerator magnets, the ceramic magnets, they produce magnetic fields. And then Ørsted discovered that current carrying wires can also produce magnetic fields. So in the previous video, the compass needle, which is a tiny magnet itself, the compass needle is a little tiny magnet. It was being torqued or pushed on by the magnetic field, which was created by a current carrying wire, right? The solenoid was that coiled wire with electricity flowing through it that produced the magnetic field, and that magnetic field pushed on or torqued the little compass needle. Now we've got the opposite. It's a permanent magnet that's producing the magnetic field, and exerting a force on a current carrying wire. So currents, electric currents, can establish magnetic fields, but they can also be pushed on by magnetic fields. It's reciprocal. And you may have noticed that when he threw this pole the other direction, he was switching the direction that the current flowed through the wire, and you saw that as a result, the wire was pushed down rather than pushed up. So evidently, the direction of the force depends on the direction of flow of the current. So let's see if we can put this all together. And to do that, it would be easier to have a graphic here. Okay, here are two wires being suspended parallel to one another. This battery is going to pass current through both of them. Let's think this through. If a current carrying wire can establish a magnetic field or be the source of a magnetic field, and a current carrying wire can also be pushed by a magnetic field, then what happens if you have two wires next to each other, both of which have current flowing through them? Well, they should both be establishing a magnetic field or act as a source of the field, but they should also both be pushed by the other's respective field. So perhaps they're going to push or pull on each other, much the way isolated electric charges can push or pull on each other. Now, here we don't have like, current is current. It's not like you've got a plus and a minus current, or do you? What you can change is the direction of flow of the current. So perhaps switching the sign of charge when you're talking about attraction or repulsion between electric charges is analogous to switching the direction of flow of current when you're talking about the forces between current carrying wires. So it's not Coulomb's law. It's not the interaction between isolated charges, but it's similar. Let's look at this interaction between current carrying wires mathematically. Before discussing this formula, we'll have to say a word about notation. It's customary to use the capital letter I for electric current. I don't know why. There's no I in the word current, but it's common. And the SI unit of current is the ampere, named after a physicist named Ampere. And 1 ampere of current just means that every second, a full Coulomb of charge flows past any given point in the wire, which is actually quite a bit of charge. Now, just like there's no I in the word current, there's also no letter B in the word magnetic, but it's customary to use the letter B for the magnetic field. Again, the magnetic field tells us the direction that a compass needle will point. It's got a direction, it has a strength, and so it's a vector quantity. And we use the letter B for that vector quantity. Okay, so when you take a class on electromagnetism, you learn how to calculate the force between current carrying wires. Here's the result. It's really the force per unit length. If these wires were longer, they would repel or attract each other with greater strength. So we really have to talk about the force per unit length. Let's look at the dimensionality of that formula. Force per unit length would be newtons per meter. In the numerator, we have the product of two currents. Each current has dimensions coulombs per second. So we really have coulombs squared per second squared. In the denominator, we have the distance between the wires. That's meters. And then there's this other constant of proportionality. Back when we were looking at Coulomb's law, there was that constant out front, K, which can be written 1 over 4 pi epsilon naught. And this constant describes the strength with which the wires attract each other. Now, if the unit of current had already been established in some other domain of physics, like if the ampere had some other definition, and then you went to measure, excuse me, the force of attraction between these two wires for a known current in amperes, this would be an experimentally determined number, this mu naught right here. But as it turns out, historically, physicists instead chose to give this number an exact value. And so in effect, they defined the ampere that way. They wanted mu naught to be a nice, easy number. I'll show you that number in a minute. So the Newton had already been defined in mechanics, in another domain of physics. They wanted this number to be nice and, well, a perfect constant. So they defined it as such, and that really defined the ampere. But since the ampere is a Coulomb per second, what they really did was define the Coulomb. All right, that's just a historical footnote there. But look at the dimensionality here. We want newtons to come out, and so we can deduce the required dimensionality of mu naught. We need to cancel the seconds that are in the denominator here. We need to cancel the Coulomb squared, and we need to cancel the meters. No, we don't. We need the meters. Those are already over there. So evidently, these are the units of this constant mu naught. And here's that perfect constant that I was describing. By definition, mu naught is 4 pi times 10 to the negative 7th. That's a suspiciously perfect number, right? It's not 8.8567923 or whatever. It's not an experimentally determined number. It was chosen to be that. And like I said, in effect, that defines the Coulomb. And this is called the permeability of vacuum, not permittivity. They both start with a P. They've got practically the same number of syllables, so it's confusing. But you've got permittivity, which has to do with Coulomb's law and the attraction between charges. And then you have permeability, which has to do with the attraction or repulsion between current carrying wires. So permittivity, think electrostatics. Permeability, think magnetism, current flowing in wires. And I'm showing you these numbers again because they will be important in our study of electromagnetic waves. These two constants play a very important role. And you really could say that they're both determined experimentally. Because like I said, if the ampere had already been defined and you didn't want to change that definition, then measuring the strength of the attraction between current carrying wires would amount to fixing the value of mu naught. So these are both experimentally determined constants. Those experiments have to do with electricity and magnetism. So this number comes from measuring the strength of attraction between electrically charged pith balls, for instance. This number comes from measuring the strength of interaction between current carrying wires. And I say permeability and permittivity in vacuum because if you embedded the pith balls or embedded the wires in a different medium like water or plastic, rubber, then these constants would take on different values. So these are the values in vacuum.
I see miracles all around me. Stop and look around, it's all astounding. Water, fire, air, and dirt. Fucking magnets, how do they work? And I don't want to talk to a scientist. Y'all motherfuckers lying and getting me pissed.
The next natural question then is, what's the real source of the magnetic field? We know that permanent magnets exist, like the lodestones, but we've also seen that current carrying wires set up magnetic fields. Which one is the true source? Is there some connection between the two? Well, there is. Here's a diagram of the magnetic field around a current carrying loop. And we'll see that this field distribution is identical to the magnetic field around a dipole, meaning a tiny little bar magnet. So the connection between the two is atoms. Every atom consists of protons and electrons, and we can think of the electrons classically, sort of, as orbiting the protons. And an orbiting charge constitutes a tiny little current loop. So this is a grossly simplified picture, and it's not quite the way things work, but there's a lot of insight in that observation that atoms are like tiny little current loops. And we know that current loops produce magnetic fields that look just like the magnetic fields around bar magnets. If I flip this sideways, it makes it a little easier to see. So here's a visualization of the magnetic field around a bar magnet using iron filings, virtually indistinguishable. So when you talk about ferromagnetic materials like iron, nickel, cobalt, you do have to talk about these things called domains within tiny little domains, and they're microscopic. Within each domain, all the atoms are lined up in a sense. Those little current loops are all pointing in the same direction, but the domains are all randomly oriented. However, if you impose an external field on that magnet, you can get all the domains to line up. So a bar magnet like this can be thought of as a bunch of little current loops with their axes all pointing in the same direction. So perhaps you could go so far as saying that moving electric charge really is the source of the magnetic field. It's clearly the source when you pass current through a wire, but even when you're talking about permanent magnets, which don't appear to consist of electric currents, when you look at the atomic scale, you're still talking about charge in motion. However, you do reach a limit with that way of thinking about magnetism, because it turns out that electrons, in addition to orbiting the nuclei of their atoms, they also possess what's called an intrinsic magnetic moment. They behave like tiny little bar magnets, even without any discernible motion of electric charge. So you can't go all the way with the charge and motion explanation for explaining magnetism. But for our purposes, let's stick with that. We'll say that electric charge in motion is what produces magnetic fields. So really, it's all about electric charge. Electric fields exist around electric charges, even if the charges are not moving. So electric charges at rest have electric fields around them. And once you put them into motion, you've also got magnetic fields around them. So the ultimate source, you could say, of electric and magnetic fields is electric charge in motion or at rest. Here's another visualization from the Falstad site. Two current loops with their currents flowing in opposite directions. And this is a little bit different than a pure dipole distribution. This would be the dipole. See how we've got these closed loops of current, or excuse me, closed loops of electric, no, I misspoke again, closed loops of magnetic field lines. Here we still have closed loops because, as I mentioned a few minutes ago, the divergence of the magnetic field is always zero. You can never have, rays emanating from a single point. That would indicate the presence of a magnetic monopole, and those just don't exist. It's always north and south together. But you do see two sets of closed loops, one from each loop of current. So I'm talking about loops of field lines, but also loops of electric current. And you can show that these repel each other, a lot like electric charges repel each other. So these loops with current flowing in opposite directions, or is it the same direction? In any case, they behave an awful lot like two bar magnets. If you bring two bar magnets close together and face their north poles together, you get repulsion. You can do the same thing with two loops of electric current. Note the analogy between, or not just the analogy, but the close correspondence between the field lines around these opposed bar magnets and the field lines around these opposed current loops. Okay, perhaps the last detail we need is how a magnetic field influences an individual electric charge. We've looked at how the magnetic field can influence a current carrying wire. Yeah, we didn't describe it mathematically. We didn't go that far, but in the MIT demonstration video, you saw the jumping wire. That was a current carrying wire being pushed clearly by the magnetic field from the permanent magnet. Well, we know that an electric current is a vast number of individual charge carriers flowing simultaneously down the wire. So how would the magnetic field influence just one charge individually? Well, this was discovered probably in the late 1700s or early 1800s. If the motion of the charge happens to be perpendicular to the magnetic field, then the formula for the force is very simple. It's right here. You just take the product of the quantity of charge, the speed of the charge, and the strength of the magnetic field. If you've taken electromagnetism, you probably had this memorized. It's worth memorizing. QVB, QVB, kind of rolls off the tongue easily. QVB. Now, if the motion of the charge is not transverse, if it's moving parallel to the magnetic field or at an angle less than 90, then you have to throw in an extra factor equal to the sine of theta. But when they're perpendicular, it's really easy like this. And then there's this so-called right-hand rule. There's lots of right-hand rules in electromagnetism that helps you determine the relative orientation between those three vectors: force, velocity, and magnetic field. This is the way I do it. I'm not even going to go over it here because we don't necessarily need this for our class, but you can use your right hand in different ways to arrive at the same result. This guy's using, or girl, I can't tell, this person's using their thumb and four fingers. That's the way I do it. You can also use the thumb, middle finger, and second finger. So if you Google it, lots of ways of using your right hand to determine the relation between these vectors. Now, with a little thought, you might be able to convince yourself that a charge subject to this type of force will move in a circle. And actually, I glossed over a very important detail. This formula gives the magnitude of the force, but we also need to know the direction because, of course, force is a vector. Well, we can see from the picture right here, the force vector is perpendicular to both the magnetic field and the velocity of the particle. And you may recall from mechanics that for an object in circular motion, uniform circular motion, that's at constant speed, the net force must always point towards the center. And that's equivalent to the observation that for a particle moving at velocity v, if there's a force which is constant in magnitude and perpendicular to the velocity, you will get circular motion. I'll just repeat that. Anytime a particle is subject to a force that's always perpendicular to its motion, and yeah, that's really the only requirement, then that force will not cause the particle to speed up or slow down. It will only cause the particle to turn. And since it can't cause it to speed up or slow down in this instance, then V doesn't change. And since V doesn't change, and presumably the intrinsic charge of the particle doesn't change, as long as the strength of the B field is uniform, then the magnitude of the force won't change. So to summarize, a charged particle moving in a uniform magnetic field, that means the arrow representing the B field points in the same direction everywhere with the same length, that particle will execute circular motion. Well, it can also do a helix, but for now, we'll just stick with the circle. Here's a newer addition to the Falstad website showing you the operation or the principle behind a direct current motor that uses a commutator. So this split ring here is called the commutator. I think most of us know that the top of the battery is the positive terminal and that the conventional current flows out of the positive terminal. So let me stop this thing and let's recognize that the current is coming out of the blue ring here and flowing back into the red ring. So it's flowing clockwise around this square circuit. And we know that the magnetic field goes out the North Pole and into the South Pole. So I can show the direction of the magnetic field like so. And let's just observe that the force on these current carrying wires, here's a current carrying wire, it's perpendicular both to the magnetic field and to the direction of flow of the charge. Because that was the observation I made in the previous slides, that the force on the electric charge is perpendicular to its velocity, and it's also perpendicular to the magnetic field. And you can see that in this picture here. The red force vector on that side of the loop, it's perpendicular to the velocity of those charges, which is, the direction of that segment of metal conductor. And it's also perpendicular to the vector representing the strength of the magnetic field. I shouldn't say the strength because it also includes direction. It's perpendicular to the vector representing the B field. You could just say it's perpendicular to the B field. And we might as well watch this thing in action. The magnetic field vectors clutter this a bit, so let me get rid of that. If you watch carefully, you can see that the red force vectors switch directions every half cycle. And that's due to the action of the commutator. The commutator causes the current to switch directions every half period. As for the assertion that charged particles moving through a uniform magnetic field will describe a circle, hopefully you find this video compelling.
Welcome to the demo prep room. We're sitting here in the dark because we're going to show you that a charged particle beam does indeed go in a circle when you put it in a uniform magnetic field. So this is an evacuated glass bulb, and there's an electron gun in it. An electron gun really just means a heated metal filament that's easy to draw electrons off of. Near the gun that you can now see glowing orange is a little metal plate that we put at a large positive potential. So that sucks the electrons up to a few hundred volts at the plate. The plate has a hole in it so that some of the electrons keep going and form a beam that continues on until it hits the glass. Now you're seeing the beam because it's exciting a little bit of gas that's inside the bulb. So you're seeing light from the gas, but it's there because the beam is shooting through the gas. So you're seeing the electron beam indirectly. Now we know that if we bring a magnet nearby, it'll deflect the beam. So here's my north-south bar magnet, and sure enough, one pole pushes it up, another pole shoots it down. If I bring it in and do these kinds of things, you can do all kinds of crazy patterns with the beam if you bring in a strong concentrated magnetic field. But what we're here to do is to create a uniform field, and that's what these two big coils are. So this is a large coil of wire on one side of the bulb, large coil on the other side. So if you put them together, you can make a reasonably uniform magnetic field on the inside. So this power supply is going to increase the current in these coils, and we'll see what pattern the electron beam takes. So here we're going to start turning it up, and you can see it's starting to curve more and more. And right now it looks like it wants to make a circle, but the radius is too big. It doesn't fit in the bulb. If I keep turning it up, more and more current, bigger and bigger B field, eventually, there it is. It makes a circle. Perfect circular motion going right back to where it started. And if I turn the magnetic field back down to zero, straight again. So there's direct visualization of the circular motion of charge in a magnetic field.
The circular motion that you just saw between the Helmholtz coils only results if the initial velocity of the charge has no component parallel to the field. So let me grab my laser pointer. On my slow computer. If, however, the initial velocity of the charge does have a component along the direction of the magnetic field, then it will execute circular motion while continuing to drift parallel to the field. And you end up with this helical trajectory. The Earth's magnetic field, of course, is not uniform. You can see just by looking at the shape of the field lines here, but over a small volume of space, let's say a cubic meter for sure, it's pretty darn close to uniform. I mean, there are large scale changes over the scale of the Earth's diameter, but in a small volume, the field would be relatively uniform. And so you can imagine any charged particles streaming in from outer space might find themselves corkscrewing in this helical fashion around the field lines. And then, you know, physicists, of course, have calculated the more complicated behavior in field lines that are, you know, wrapping up like this, leaving the Earth, terminating at the Earth. I shouldn't say terminating because magnetic fields don't terminate. They just swoop right through the Earth. You get this bottleneck effect where the charges corkscrew towards one end, and then I believe they turn around and go back the other direction. But in the process of corkscrewing like that, they're going to have collisions with other particles high in the atmosphere. I don't know the details, but you get this remarkable effect called the aurora. I think it's borealis in the north and australis probably in the south. So if you've ever witnessed the aurora, then you've also seen confirmation of the circular motion or helical motion of charged particles in a magnetic field, a magnetic field that's close to being uniform. All right, that brings us just about to the end here. For those of you who have not taken a class in electromagnetism, I hope I've given you at least somewhat of a feel for the meaning of electric fields and the meaning of magnetic fields. We don't need to know how to calculate those fields the way you would learn in an actual class, but as long as you know their physical significance, you should be able to use them in the subsequent material. We're going to describe electromagnetic waves. Now, those waves were first predicted in the mid-late 1800s by a famous physicist named James Clerk Maxwell, and he built upon the theoretical results from those that came before him. So this was a 100+ year intellectual struggle to understand the laws of electricity and magnetism. These are kind of hallowed results in the history of physics. There are 4 so-called Maxwell equations, and each of them has either its own name or a description. So let me just briefly motivate each of these. At the beginning of this presentation, I showed you isolated electric charges, and we looked at how the field lines look like they're diverging from that point charge. They're all pointing away. If the charge was negative, they would all be pointing towards the charge. This statement says something precise mathematically in those terms, or it expresses that observation mathematically. It basically says that electric fields appear to be diverging from points where there's electric charge present. This would be the electric charge density. Now, if we were looking at the electric field in a vacuum, meaning no matter, especially no charged matter, then the right side of the equation would be 0, and that would say that the divergence of the electric field was 0. So you might have a uniform field where all the arrows are pointing in the same direction, but you would not have a field that looks like it's diverging from any one point. If it did look like it was diverging, that would indicate the presence of electric charge. Now this one's a little trickier because some of you have not yet taken your 3rd semester of calculus. You don't know about vector curl, which is a type of 3-dimensional space derivative. It's kind of like d dx, but in 3 dimensions. Now, the GIF at the very beginning of this presentation showed how if you create a magnetic field that pierces a loop, and that magnetic field is changing in time, you may observe current flowing in the loop. That's called induction. Basically, it just says if you can change in time the magnetic field that's piercing a loop of current, you can cause current to flow. Did I say a loop of current? I meant to say just a loop of wire, any closed conductor. By changing the magnetic field piercing that loop, and that's what we call flux, you can cause electricity to flow. So this was super important observation in the history of science because it led to the development of electric motors, electric generators. This one doesn't have a name. It's not named after any particular individual, but I talked earlier about how the magnetic field lines for any source of magnetism, they're always closed. You can never break a magnet in half and isolate just a North Pole or just a South Pole. If you could isolate just the North Pole, presumably you could have field lines diverging away from that pole. And if you drew a circle around the North Pole, you would have field lines going out, but none going in. So you'd have a net flow outwards, but it doesn't work that way. Anything that goes out comes right back in the back door. And so mathematically, we say that, or we express that by saying that the divergence of the B field is 0. You'll never find a magnetic field where it looks like all the field lines are coming out of a single point. That will never happen. Well, I shouldn't say never, but it's never been observed. If it did, it would indicate the existence of some sort of magnetic charge. See, this charge density is electric charge density, and such a thing does exist. And so the right side is not 0. But as far as we know, there are no magnetic monopoles, which is why the right side here is 0. The B field never diverges from any one point. It's a fundamental asymmetry between these two fields. Many theorists over the years have had a compulsion to try to force a symmetry here. It would kind of be nice aesthetically if we could find a magnetic charge density, because then these equations would be symmetric. The 4th Maxwell equation here has also been demonstrated in this presentation. You saw examples of current carrying wires establishing magnetic fields. And you may have noticed for the case of the solenoid, which is the coil of wire, you may have also seen in one of the videos the magnetic field around a straight segment of wire. The field tends to swirl around the wires. And that's basically what this first part says. The curl of the magnetic field, just think of it as the swirl. The swirl of the magnetic field has as its source the flow of, this is electric current density. This J is related to I, the number of coulombs per second. It's the distribution of I over a surface. So if you have current flowing, electric current, then at that same location in space, you will also have a swirling magnetic field. So with the exception of this term here, everything here was known by the early to mid 1800s. And I should say one or two more words about this stuff, specifically this part and this part. No, really just this part. I'm going to get to this one in a second. What does this equation tell us? If your magnetic field at a particular point in space is changing in time, so if it's not constant, if there's any change at a particular point in space, then there must also be an electric field. The rate of change of the magnetic field in time at a particular point in space tells us something about the spatial distribution of the field at that point. Now, the left side can only be zero if the right side is zero. So if the magnetic field is changing at all, then the left side isn't zero. And, this isn't totally obvious, but if a vector field has a curl, if it has any kind of curl, then that field is not zero. It's like there's got to be something happening. There has to be some sort of E field if the right side is not zero. And what that means is anytime B is changing in time, you will also find an E field at that same point. And a lot of authors or books phrase that by saying that a changing magnetic field creates an electric field, like the presence of dB dt, or dB dt not being zero, causes the electric field to exist. And I think that's a little misleading because ultimately the source or the cause of both of these fields is electric charge, either at rest or moving. That's really the source. And if you've got electric charges moving on the surface of Earth and they're going to set up a magnetic field over where Mars is, for instance, Mars is really far away. It takes, I don't know, minutes, half an hour for radio waves to get to Mars from here. So whatever fields appear at Mars due to currents on Earth, they're going to take a while to get there, but ultimately the source of those fields or the cause was the moving electric charge here on the surface of Earth. So I don't think it's particularly fruitful to think of E being created by a change in B, or vice versa. Down here, you see this equation suggests perhaps that B is created by a time derivative of E. So a lot of people will say the same thing. A change in E in time will create a magnetic field. And so perhaps if one can create the other, and then that one can create the first one, perhaps they can sustain one another outwards in space. So you just want to keep in mind that ultimately the cause of both of those fields, I would say, is the electric charge that was moving or at rest. Okay, this second term escaped physicists for a long time. And the reason for that is it was difficult to detect in a laboratory. Nowadays, we can make electromagnetic waves, and this has been done since the early 1900s. We can make radio waves where the electric field is changing really rapidly, a very large time derivative. But in nature, such a thing is more rare. I don't know if I should say that, but that was the reason why this term had not been discovered in the laboratory, not so easily discoverable. But Maxwell, and I should have pointed out that this first half of this equation is often called Ampere's law because Ampere was the one who had discovered it, much like how Faraday had discovered the law of induction. Maxwell, by adding this last ingredient here, paved the way for the discovery of electromagnetic waves. So we'll see soon that if you take these four results, throw them together in a salad bowl, mix them together, pour some dressing on there. By dressing, I mean throw some vector calculus at it. Out plops, I'm not going to say it, but a very familiar equation. So we'll look at that in the next presentation. Let me just point out one last symmetry here. See the the curl of the magnetic field depends on the, excuse me, the time derivative of E, and the curl of the electric field depends on the time derivative of B. So these two equations are symmetric in that regard, but we're missing a second term here. See how this first equation tells us that the B field depends on the flow of electric charge. Wouldn't it be nice if an equivalent term appeared here so that the curl of the electric field depended on the flow of some magnetic charge? Well, that term is absent for the same reason that the right side of this equation is 0. Remember, as far as we know, there are no magnetic monopoles. A flow of magnetic charge, that would be like a bunch of north poles without their south poles flowing through a wire or flying through space. And we know of no such thing. So this term is absent from Faraday's law. Another irritating aspect of these equations for those who would like to see a more aesthetic symmetry. And lastly, maybe you're thinking, okay, so charges get pushed by electric fields, and they also get pushed by magnetic fields. And in order to be pushed by magnetic fields, the charges need to be moving. If you go back to the formula QVB for magnetic force, if the speed V is 0, then that implies no force. But, you know, we think about relativity and frame of reference. I might think that a charge is moving, but somebody in another frame of reference could say it's not moving. Like, I always go back to this example, but if you're sitting in your chair or your sofa on Earth, you might think that you're not moving, you're at rest. But somebody on Mars looking at you through a giant telescope would say, actually, you're flying through space at 30 kilometers per second in a giant circle around the sun. So what does it even mean to talk about an electron that's at rest or not at rest? Because if one observer says it's at rest, another observer will say it's moving. So this is starting to muddy the waters and blur the distinction between an electric field and a magnetic field. It would be nice if you could describe the action on electric charges with just a single mathematical object. So rather than using two vector fields, the E field and the B field, wouldn't it be nice if you just had one object, one mathematical entity? Well, there is such a thing, and it's called the electromagnetic field tensor. And not coincidentally, it has 6 independent components. You'll notice that the diagonal elements of this 4x4 matrix, or you could say, excuse me, what is this, a rank 2 tensor? Yeah, I'd have to think about that. So these are all 0. And notice that the entry in the second row, first column, is the same as the entry in the first row, second column, with the exception of a minus sign. So once you've fixed this number, you already know this number. It has to be the negative of that number. Same goes for first row, third column, and what is this, third row, first column. Right? This number is just the negative of that number. So if you look carefully here, there are actually only 6 independent components. Once you've determined Bx, By, and Bz, then you of course know what negative Bx is and negative By, etc. Same goes for the electric field. So it may be a 4x4 matrix with 16, positions, but really only 6 of those numbers are independent. And that's generally true of what's called an anti-symmetric tensor or anti-symmetric matrix. Anti-symmetric because the entry in the second row, first column is the negative of the entry in the first row, second column. Like 2, 1, 1, 2, they're negatives of each other. That's an anti-symmetric tensor. So you could think about 2 vectors, E and B, each of which have 3 components. That's 6 total, 6 independent quantities. Or you could think about this single object, the field tensor, which also has 6 independent quantities. Now, don't be scared by this thing. We are not going to be using this. I just thought you might find that interesting.
Whoa, whoa, whoa. Wait. Yeah, that did it. Yeah,